Counting is fundamental. Humans begin doing it at a very young age, and many non-human animals possess some degree of numerosity. That's the ability to grasp or recognize approximate numbers and relative amounts. This fundamental ability is the basis for much of modern life, especially science. Measuring distance is counting in units of distance, and weighing something is counting in units of weight, and populations are measured by counting units of individuals. Of course, sometimes it's hard to know exactly how many things there are, and this leads to uncertainty, which is an integral part of any science, and it probably feels fairly intuitive. In daily life, we usually just accept the uncertainty and estimate. Scientists go a step further, though, and try to estimate the uncertainty itself. That's why scientific values are often reported as some number plus or minus another one. But imagine that the things that you're trying to count may not even exist in the time that you think you observe them. That's what it's like to count things that happened in the past. And it makes counting something as simple as counting so much more interesting than you may have thought. Take, for example, counting extinct animals. By around 10,000 years ago, nearly all mammal species in North America with a body size greater than 44 kilograms had gone extinct. We call this group of species megafauna because they were so big. And examples include famous Ice Age animals like the woolly mammoth or saber-toothed tiger and giant ground sloth. The reasons for the extinction have been debated for decades, but the two most commonly investigated possibilities are climate change and human activity. The fossil record for many of the... The reason for the extinction have been debated for many decades. As I said, the fossil record for many now extinct North American megafauna ends near the boundary between the Pleistocene and Holocene epochs, about 11,700 years ago. It was the end of the last ice age, and glaciers were receding. The Earth was warming, and as a result, the environment was changing a lot. So it's no surprise that many scientists suspect climate change might have been involved in the extinction. In particular, two major temperature swings occurred. The first was called the Bowling Alurod, and during this period, the Earth's temperature rose by up to 5 degrees Celsius in a century or less. This rapid warming was followed by a cooling trend of a few hundred years before suddenly temperatures dropped by about 10 degrees Celsius back into nearly glacial conditions, a period called the Younger Dryas. One or both of these major climatic events may have been responsible for the disappearance of the megafauna. Around the same time, however, human presence seems to have been expanding on the North American continent. The number of known archaeological sites appears to increase from the earliest arrival of humans, at least around 15,000 years ago, across the Pleistocene-Holocene boundary, which suggests that populations may have been growing. A new class of projectile points also appeared all over the continent. This new point type, the Clovis Point, is highly distinctive, and it's thought to represent a significant change in technology geared toward big game hunting. These two archaeological observations, an increase in human activity and new hunting technology, could have coincided with the disappearance of the megafauna, which has led many researchers to suspect that human overhunting contributed to or caused the extinctions. Determining whether one or both of these explanations is correct hinges on our ability to count. Testing whether humans, climate change, or both drove numerous megafauna species to extinction must involve comparing changes over time in at least two quantities. These two quantities are, on the one hand, changes in the numbers of megafauna, and on the other, changes in the number of humans. We have to count how many of each there were at a series of times leading up to and including the potentially relevant climatic changes. Of course, we can't go back in time and take a census, so instead we need to count things that we can observe, like megafauna fossils and archaeological sites, and we use these as proxies for the real quantities of interest. Then we need to compare changes in these proxies to one another and to changes in climate records. These comparisons are necessary for figuring out whether a relationship may have existed between megafauna extinctions on the one hand and humans or climate change on the other. Like many counting exercises, though, there are uncertainties that make counting long-dead animals difficult, and many of these are common across multiple domains. It can be difficult to count things, for example, when they're too numerous to count explicitly, like grains of sand or stars in the sky. Some things also move around a lot, which makes it hard to observe them for counting or to know that an individual item hasn't been double counted. A good example here would be herd animals that migrate over sizable areas. Still, other things are hard to detect at all, even though they may be abundant, like neutrinos. These are subatomic particles with no charge and only a tiny mass. There are lots of them in the universe. In fact, they may be one of the most abundant particles around, but their lack of charge and small mass means they don't interact with anything, makes them very hard to detect. Archaeologists trying to count megafauna run into similar challenges. There may be an enormous number of fossils and archaeological sites in North America to find and count, and only a portion of those will so far have been recovered. Preservation is rare. The situation has to be just right for the evidence of human activity or animal remains to be covered and protected in sediment. Even then, fossilization can only occur under a specific set of environmental conditions. There's also an enormous area to search. North America covers roughly 24.7 million kilometers square, so walking over all that territory just to look at the surface would take a long, long time. Of course, most fossils won't be found laying about on the surface anyway, so the search would have to include digging, and only a sample of the potential fossil-bearing sediment could ever plausibly be examined. To deal with these sorts of challenges, scientists use estimation and statistical sampling to derive counts and corresponding uncertainties. For example, if you were trying to count all the grains of sand on this beach, you could scoop up a sample, count the grains in that sample, and then calculate the approximate number of similarly sized scoops. Then a bit of multiplication, and you'd have an estimate of the total number of grains. Of course, one scoop may have more or fewer grains than another scoop, and that can happen because the scoops can be slightly different sizes. And it can also happen if the individual grains are different sizes, which means that different numbers of grains may fit into the same scoop depending on whether big grains or small grains happen to be picked up. Consequently, the estimated grain totals may differ depending on the samples. So scientists would typically repeat that sampling process multiple times and take an average. Similar sorts of strategies can be used to sample anything that scientists are interested in counting, including archaeological sites and megafauna fossils. For archaeologists, though, there's an additional source of uncertainty that adds a dimension to the counting problem, and that source of uncertainty is chronological. Estimating the number of megafauna fossils, or animals rather, that were alive at a series of times in the past means that we have to determine how many fossils date to each time. And to do that, of course, we need to first estimate the age of each fossil, which we're happy to assume corresponds roughly to when the animal was alive. And the age estimates are also then required for the archaeological material used as an indication of the number of humans. When studying the distant past, we have several tools available for estimating ages. These chronometric tools, like radiocarbon dating, for example, come with their own uncertainties, though. And actually, chronometric estimates typically are also the products of counting exercises themselves. But suffice it to say, we can estimate something like an average age for a fossil or archaeological site. That average describes the central age of a distribution of possible ages, and that distribution describes our uncertainty about the true age. Well, the central or the average age is in a sense the most likely compared to the other candidate ages. The other ages are still possible, and in fact, somewhat paradoxically, it can also be shown that the real age is probably not the average. Take this distribution, for example. It's a normal distribution, commonly called a bell curve because of its shape. Imagine that this distribution represents our uncertainty about the age of a given fossil. The height of the curve indicates the relative likelihood that the fossil dates to the corresponding time on the horizontal axis at the bottom. That axis represents the domain of the distribution, which comprises all of the possible ages. The area under the curve corresponding to a given range of ages is proportional to the probability that the true age falls into the relevant interval. So, for example, the dark blue region here indicates the mean or central age of the distribution. Compared to any other region under the curve defined by an interval of the same length, like this lighter blue region, for instance, the central darker blue region has the greatest area. This means that ages contained in the dark region are the most probable, relatively speaking. But when compared to the rest of the distribution all at once, the reverse is true. The ages in the central region are now less likely. Instead, it's more likely that the true age is not in the central region at all, because the area outside of that region is much larger, relatively speaking. Nevertheless, the distribution still gives us important information about the set of most likely ages. It says that the most likely ages are closer to the middle, the mean, and less likely ages are closer to the lower edges. These are also called the tails. Imagine for a moment that we can turn this distribution into a sort of weighted die and then roll it. This is called sampling the distribution. The die faces in this case would represent the probable ages in the domain of the distribution, and they would be weighted in a way that corresponds to the height of the distribution. Again, ages chosen at random by rolling this imaginary die are represented here by the falling circle. The result of the die roll is indicated by the location of the circle when it hits the horizontal axis. If we let the circles stack up over time, essentially count the number of times each possible age is sampled, we can see that the results come up in proportion to their probabilities. The ages pile up towards the center of the domain, forming a sort of bell-like shape that mirrors the distribution. This property of statistical distributions makes it difficult to justify using only the mean age of a fossil when we're trying to count it. Other ages, like these, are probable too. So we have to consider all of the possible ages when counting things that happened in the past. The sampling simulation that we just looked at, though, was only for a single fossil. So now imagine that we have several fossils, each dated with some uncertainty. Again, the falling circles refer to probable ages. Each time the distributions are sampled, this is like rolling a set of weighted dice, a couple of interesting things happen. First, the temporal order of the fossils occasionally changes. This happens because the distributions representing chronological uncertainty overlap. So sometimes the imaginary die rolls come up with results that reverse the order of things. Second, and most importantly, the shape of the series of counts as a whole, that is, the rises and falls in the numbers over time, can change, sometimes dramatically. Whether the counts increase, decrease, remain constant, or fluctuate through time depends on the specific set of dates that are sampled. Because of chronological uncertainty, then, there are many different probable through-time patterns for counts of anything that happened in the past. It's like there are many probable pasts instead of just one. This means that there may be multiple answers to important questions like when did the numbers of megafauna begin to decline? Did that decline coincide with changes in the numbers of humans? Or did it coincide with changes in climate, or both? Answering these questions comes down entirely to the core challenges that archaeologists face when trying to do something as seemingly simple as just counting bones. When archaeologists count something, we not only have to estimate how many things there were, but also when they were.